Hey everybody, Chris here from AV.technology. I'm here with Ryan. We thought, well, it's the first time seeing Spectra in the flesh. Do you want to give us the quick sort of rundown of exactly what it is and why it's a game changer?
Okay, so Spectra in itself is a game changer because we're changing how regulators think about wireless audio. Okay, in the past, regulators have thought wireless microphones to be a one single carrier of 200 kilohertz. Okay, we've switched that to becoming a wideband audio carrier of 8 megahertz.
Right.
Now, why have we done this? Two reasons. Firstly, capacity. In a 200 kilohertz carrier, you can only fit so much data. And when these regulations were written or composed, it was to do with the fact that we were transposing audio on top of a radio frequency, analog audio, because it fitted inside.
Yes.
When we switched to becoming a digital carrier,
yes,
you then have to change that carrier to become a modulation scheme. QFSK we were using, for example, but that only gives you 4 points of data around a QFSK carrier. Okay, it's not enough.
Right.
We have to compress at that point.
Right.
So you're compromising your audio quality at that point.
Right.
So you have to go wideband in the digital domain. So if we're going to go wideband, let's go 8 megs, TV channel.
Sure.
You then have a much bigger carrier or a much more amount of data that you can then transmit and receive over that carrier. So we have within that carrier the ability to have, let's say, 128 time slots.
Yes.
Each one of those time slots can be an audio link, or it can be multiple time slots per audio link, okay, depending on the resolution, the quality, or the latency,
Sure.
which is all scalable.
Sure.
Okay, but also by having an 8 meg carrier, you're reducing what we call a fading effect. If you take a standard 200 kilohertz body pack, you have a signal that's transmitting from here to the antenna. However, this is also transmitting off the floor, off the ceiling, off the walls, okay? If at 200 kilohertz it receives a signal point to point and 180 degree phase cancellation will stop the RF from being picked up here.
Yep.
Okay? At an 8 meg carrier, this fading effect is far less pronounced. You're talking minus 50 dBm, minus 55 dBm of a loss.
Okay.
At an 8 meg carrier, it's maybe minus 10, minus 15. The system can cope with that. So
Yes.
these are the main two reasons why we developed wideband. So data capacity
Yes.
and fading.
Right.
Okay. Then from that point, well, how do we use our time slots? What do we use them for? Do we use them for more channels, more links? Technically, we're talking 64 links here, so 32 in, 32 out.
Right.
Because the pack is not only a wireless microphone, it's also an in-ear monitor in the same pack.
Yeah.
That's a fundamental difference for the audio industry.
Sure.
Massive difference. Okay?
Yeah. I guess that's the key sort of physical.
When you look
that
at the
people
hardware,
immediately
yes.
latch onto it and go, oh wow, it does both.
Yes.
But hearing you kind of talk about the fundamental sort of platform underneath that makes that possible.
Yes.
That's
yes.
that's what's kind of truly interesting from an engineering point of view, I suppose.
Yes, I mean we're exciting both. You know,
Yes.
we're exciting the engineers by the technology that's behind it, as you just pointed out. But we're exciting the user because it's less physical hardware that they have to wear,
For
right?
sure, for
Okay.
sure.
Think of the broadcast industry, for example, where you have some news readers that have got sometimes 2 microphones and an in-ear monitoring system. That's weighing their trousers down as they're sitting there reading the news. You know, no longer is that the case. They can have one single pack. Well, dresses, yes.
Right. So I want you to keep talking. So what are from the response that you've had here, like as far as an application perspective, is it entirely predictable, or are you finding people going, this is why this
It would be naive of us to predict every use case.
Sure.
Right? We are at a starting point here. This will be our development going forward. And this, as you see the physical, this is the base station here with the I/O part of it and with the control. There is no RF component in here. All the RF is done here.
Right.
That's a transceiver.
I see.
At the moment, we have this as the pack.
Sure.
Within the next 12 months, we will also have a handheld.
Yes.
But you come back to me, you tell me, what else do you need?
Oh, why not half that size?
Okay, well, maybe not half, but less, yes. We will work on this. We know that that's a want, particularly in live theatre and opera.
Sure.
Yes. We're already looking at that.
And as far as spectrum goes, is there any speed humps or things to be considered, like sort of in the Australian market?
Yeah,
know much about?
already type approved in Australia.
Okay, right.
Andreas Vilcek, who's in charge of our spectral affairs department, has been going around the world for the last
You have
3
a
years.
spectral affairs department.
We do. We do.
It sounds very secret police.
Well, yeah, you know, it's when you're talking RF, it is a little bit secret police. But he's been going around the world, going to the ITU, the International Telecommunications Union, going to their WRCs every 5 years, which is the World Radio Communications Council or conference, ensuring that the regulators are aware of this.
Yes.
Okay. Yes, there's been speed bumps to get to that point.
Yep.
Okay. We're still working with regulators to get it approved everywhere, but 99.9% of the world is already approved. FCC last year, for example, Ofcom in the UK already done, Australia done. Yep. Already done, but there was speed bumps because of this restriction of, it has to be 200 kilohertz. Yeah. It's not, it's 8 meg.
Okay. Yeah, and I guess in super crowded spectrum, like if you're talking about West End or if you're talking about Broadway, it can look after itself.
You are responsible for the physical input of it. Let me show you the spectrum analysis that we've already done here at the show. It's quite congested.
Yeah.
This is my RF scan of the UHF spectrum that I'm operating in. This is 470 to 694 megahertz. You can see here how busy it is. Each one of these carriers is someone else using the space. This is a traditional wireless microphone, 200 kilohertz wide. This is us. We're an 8 meg carrier inside here. But I can pick where that goes.
Yep.
And I can pick two.
Right.
I don't just have to have one.
Right.
I can have a second carrier in here somewhere.
Right.
And now with the latest development, we can use 1.4 gigahertz as well. Not everywhere in the world yet, but it's a frequency range that is far less congested. So that you can then start thinking, okay, I can get another 64 channels in the 1.4 gigahertz range in the future.
Right.
And you can operate both out of the same base station. It's different antennas and different packs, yes, but the same base station could be running both at the same time if you wanted it to. Yeah?
That's cool. Is that about it, Ryan? Like, that's pretty good.
I want to give you a little bit of information about footprint.
Okay.
About real estate. Okay.
Yes.
If you look at what we normally have for, let's say it's a 16-channel wireless microphone system, you have a rack space that's this much.
Yeah.
You've condensed that into this.
Yeah.
You can get that in your suitcase.
Yeah.
Can't get that in your suitcase.
No.
Okay. So physical hardware is a key contributing factor to what the success of this product will be. You think about an OB truck where they have a requirement for a lot of wireless microphones and a lot of in-ears. There's not a lot of space, not a lot of real estate in an OB truck. So if we can get that down into that size, win-win. Yeah.
Totally.
But also because there's less physical hardware, our manufacturing costs are less. Cost to the consumer or the customer of this product is less. You look at this is probably 4 times the cost of this. Same system. Less antenna requirements. No coax cable. This is a point-to-point network connection. The transceiver is here.
Yep.
So you no longer need to have coax.
Yep.
You can just put a network cable up to 100 meters into one of the 4 antenna ports here.
And so there's the cable length is not the same.
So you don't need to calculate it anymore. It's just data that you're pumping down it. It's not RF that you're pumping down the cable anymore. So standard network capability. So if you say a Cat6 cable, for example, will do 100 meters. However, you can still convert to fiber.
Sure.
We've ran up to 4 kilometers on fiber, still cohesive. What you cannot do is have it part of a switch network. There's no IP here. It's point to point. It's layer 1. Okay. And the reason behind that is because switches will add latency.
Sure.
We can't have latency in the system. It needs to have point-to-point, real-time communication.